Okay, so today we are going to discuss about protection and deprotection for aldehyde and ketones. Protection, deprotection for aldehyde and ketones. So the aldehyde functional group can be written as where R is any alkyl group. To represent ketone, you have to replace this hydrogen with another alkyl group. And this is how you can write a ketone functional group. So this is about how you represent aldehyde and ketone. Now what is the protection method? So for example, suppose I have a aldehyde or any ketone and I want to protect it. So you can use a 1,2 diol system. Right? So this is a 1,2 diol system. You have to use a catalytic amount of H plus ions also. You can also protect this aldehyde or ketone with a 1,3 diol system. So this is a 1,2,3 diol system. You also need a source of H plus ions. So the product, if you use 1,2 diol system, the product will look like this particular acetal or ketal. If you use 1,3 diol system, the product will look like this one. So the mechanism for this particular reaction I have already discussed in detail in my previous video, where I talked about protection and deprotection of diols. And if you have watched that video, you will also be knowing that if you are using 1,2 diol system, you have to use a cis conformation. And it doesn't matter if you are using 1,3 diol system, it does not matter whether you are using cis or a trans system. So make sure you watch the mechanism for this particular reaction in my previous video. And what about deprotection? Suppose I want to get back my aldehyde or ketone. So I have to use a strong acidic media in presence of water. So this is how you can deprotect your aldehyde and ketone from acetal or ketal. So this is a acetal. If you are starting from aldehyde, it will be named as acetal. If you are starting from ketone, it will be named as ketal. This deprotection mechanism also I have discussed in my previous video. So this is about the protection of aldehyde and ketones using diol. And this is how you deprotect. You have to use a acidic media for it. So now let's go ahead and see what are other methods of protection for aldehyde and ketones. Okay, so I'm giving you one example. So I have a starting material. This particular ketone, and I'm reacting it with titanium tetrachloride, a Lewis acid, in presence of methanol and triethylamine as a base. So what is the product? So the product will be the protected ketone. OMe and OMe. So what is the mechanism for this particular reaction? So we have a ketone and we are using titanium tetrachloride to activate this carbonyl system. So this oxygen is now bonded with titanium metal and will bear the positive charge at oxygen. Right? So this titanium tetrachloride was used to chelate with oxygen and activate your carbonyl center. Now we have a methanol in the system. So at this point of time, the methanol will come into picture where oxygen lone pairs will attack at this carbonyl, will open up this C double bond O bond. So you have generated oxygen with titanium, and you have a O, hydrogen and a methyl, and this oxygen have 3 bonds, so it will bear a positive charge. Now this oxygen lone pair will take away this hydrogen, so it's an intramolecular hydrogen transfer reaction, and this oxygen will get neutralized, right? So this is how you generate this particular intermediate. O, and we have a methyl group. Now this group is a positively charged, and when oxygen lone pairs will form a double bond here, this is going to leave as a neutral species. So you will generate another carbonyl system, but this time we have a OMe here. Once again another methanol molecule will come. In similar fashion, it will attack at this carbonyl, will open up this bond, and this will generate OMe, OMe, and here we have a hydrogen with plus charge. Now at this point of time, we have a triethylamine as a base. So this base will take away this proton, neutralizing oxygen, and this is how you are getting your final product, deprotected ketone. So this is the mechanism for this Lewis acid catalyzed ketone protection using methanol and triethylamine as a base. Okay, so before I begin further, I want you to take some notes. So you need to know the order of reactivity. We have an order of reactivity for aldehyde and ketones. Okay, so the most reactive is aldehyde. Then we have a ketone in the list, right? Then we have a cyclohexanone. Then we have a cyclopentanone. And finally we have a alpha beta unsaturated ketone. So this is the order of reactivity. So you need to know that aldehyde is most reactive, followed by ketone, followed by cyclic form. So the acyclic version is more reactive than cyclic version. Then we have a cyclohexanone followed by cyclopentanone, and the least reactive is alpha beta unsaturated carbonyl system. I also want you to know, so this is the first thing I wanted you to know. The second thing is that the 6-membered ring, okay, the 6-membered ring will hydrolyze faster than 5-membered ring when it comes to deprotection. So suppose I have 2 reactions where I am doing deprotection for this protected product, and I am getting acetone and a 1,3-diol system. And in the second case, I have a 1,2-diol system, and I'm doing deprotection to get acetone and 1,2-diol. Okay, so both the reactions are carried by acidic media. So this is a 6-membered ring, right? 1, 2, 3, 4, 5, 6, and this is a 5-membered ring. 1, 2, 3, 4, 5. So this is a 6-membered ring, and this is a 5-membered ring. And we know 6-membered ring will hydrolyze faster than 5-membered ring. Suppose you have to do a comparison. Suppose the rate of reaction for this reaction is K1, and rate of reaction for this particular reaction is K2. So which reaction will be faster? So if you know this particular statement, you will know that K1 will be faster than K2. Okay, so I also want you to know that the acyclic ketal, okay, so the acyclic acetal or ketal will cleave faster than cyclic ketal, cyclic acetal or ketal. Let me explain you by giving you one example. So for example, I have a molecule this particular molecule, and I'm doing selective deprotection of any one functional group. So which diol will cleave first? Okay, so you need to know that acyclic will cleave faster than cyclic. So this is a acyclic and this is a cyclic system. So what is the product? So we are going to selectively deprotect this part. This will generate an aldehyde here. So here we have 1, 2, 1, 2, followed by this particular protection will remain intact. So this is the product for this particular reaction. So this is very important when it comes to a competitive exam type of questions where you have to do selective reaction. So you need to know that acyclic acetal or ketal will deprotect faster than the cyclic product or cyclic protected diol. So this is the product for this particular reaction. Okay, so here is a question for you. We have a starting material, acetone, and I am reacting it with trimethyl formate, which can be written as HCOMe3 in presence of H plus ions. So what is the product? Okay, so let me give you the product and you can try out the mechanism for this reaction. Let me draw it as a cyclohexane. So it is a cyclohexanone. Okay, so this is the product. So feel free to pause the video and try to solve this reaction mechanism where you are reacting cyclohexanone with this trimethyl formate group in presence of catalytic amount of H plus ions, and you are protecting your ketone by forming a acyclic. Okay, so this is not cyclized one, this is an open one. So this is a acyclic starting from ketone, so acyclic ketal. So feel free to pause the video and try the mechanism for this reaction. Okay, so we have this trimethyl formate group which can be written as HCOMe3 fine. We have acidic medium, so this oxygen lone pairs will grab this proton and now this OMe is a good leaving group. So another oxygen lone pair will push out this whole group into a neutral methanol molecule and will give me H, C double bond O, Me bearing positive charge. Here I have another OMe group and we have just removed a methanol molecule. Okay, so we have a cyclohexanone and we have a methanol, correct? So what happens is, the methanol will come into picture. Will attack at this carbonyl, will break this C double bond O bond, and you have oxygen bearing negative charge and O, hydrogen and methyl group with positive charge. So now you have this. Now at this point of time, this oxygen will do the intramolecular hydrogen transfer to generate OH with OMe. Now this oxygen will form a double bond here, and this oxygen can do hydrogen bonding with H plus ions. We have lots of H plus ions in the solution. Okay, and this whole group can leave out as a water molecule, correct? So we have generated C double bond O, Me with plus charge. Now this reaction will keep on generating methanol for me. So another methanol will come, will attack at this carbonyl system, will open up this bond, and you have a O, Me and OH, Me bearing positive charge. Now you have just removed water here, and water is a amphoteric in nature. It can act as an acid and a base. So here it will act as a base, will take away this proton, and by removing this proton you have generated the final product. So this is the mechanism for this particular reaction. So why we are using this trimethyl format? The reason is simple. We want methanol. So all it's doing is it's generating methanol for me, which later attack at this carbonyl system generating OMe, and further once again this C double bond O generates and another methanol attacks to form this final product. Okay, so here is one question. I am reacting this particular ketone with triethyl formate, okay, in presence of catalytic amount of HCl. So what is the product? So this reaction is similar to the previous question. So we know the product, right? All we have to do is protect this ketone with the ethyl group, OET group, simply because we have used a triethyl version here. So the product will look like OET, because we have used OET version, so here OET will come. So we have formed a acyclic ketal and we have protected this particular ketone. Okay, so suppose another question, I have a benzaldehyde. And I'm reacting this with cesium chloride and a methanol. So what is the product? So this question is very similar to the first question I discussed, Lewis acid mediated protection of aldehyde group. So this cesium will do chelation with this oxygen, will activate this carbonyl system. Later this oxygen lone pairs of methanol will attack and will form the acyclic acetal product, OMe and a OMe. So this is the product for this particular reaction. Okay, so this is an interesting question. So this is my starting material. Okay, and I'm reacting it with a diol in presence of catalytic amount of H plus ion and water. So the product we are getting is little unusual. So the product, if we are expecting is, we are expecting the product will be of this kind. Okay, so we know that ketone can be protected by using diol by forming this cyclic ketal. Okay, so we expected this product, but the observed product was different. So the observed product was, so we indeed did the protection of this ketone, but the double bond position shifted, and this is the product we got. So what is the mechanism, right? If the product was this, the mechanism was pretty straightforward. Just protect your ketone. But the double bond position has shifted from this center to here. So feel free to pause the video and try the mechanism for this reaction. Okay, so let's see the mechanism. So this is my starting material. We have a acidic media, right? So this oxygen lone pair will take away this proton. So now we have an activated carbonyl system. Okay, now at the next step, now the diol will come into picture. So this is my diol. So this oxygen lone pairs will attack at this carbonyl system, will open up this C double bond O bond, and we will have something like this. So now we have OH, and we have oxygen, CH2CH2OH, right? Then furthermore, this oxygen lone pairs will form a double bond here, and this OH group will leave out as a water molecule. This oxygen can do chelation with this proton and leave out as a water. Okay, so this will generate C double bond O, CH2CH2OH. Okay, so now here is the key step. This oxygen will also get a positive charge. Now in next step, so we have a water. It can act as a base, and it will take away this proton, will form a double bond here. This bond will migrate here, and this oxygen will get neutralized. So this is how the position of double bond shifts. So now we have a double bond at this position, and this double bond is shifted here, and this C double bond is now a single bond, and this group still have CH2CH2 and a OH, correct? Now this oxygen lone pair will attack at this carbon. Once again, this bond will shift here, instead of shifting, it will directly take away H plus ions, correct? And this will generate the product we are looking for. The reason I did not did the further transformation is because we want this particular product. We want the shifted double bond. So that's why when this oxygen attacks here, directly this double bond will take away proton, and this double bond will be intact, and this is how we get the final product. Okay, so let me just recall once again what we did. So we are doing protection of this ketone. We are expecting that this is the product we are going to get, but the product we are getting is the same, but the double bond position has shifted. So this is the mechanism. So in first step, this oxygen lone pairs will grab this proton and this carbonyl will get activated. Then the oxygen of diol will attack at this carbonyl, will neutralize oxygen, and you get this particular molecule. Furthermore, this oxygen lone pair forms a double bond here, leaving this OH group will generate this particular molecule. Water can act as a base, can grab this particular proton, will form a double bond here. So this is the main key step. So water grabs this proton, form a double bond, this double bond shifts here, neutralizing oxygen, and you get this particular intermediate, and at the last step, this oxygen lone pair attacks and this double bond take away H plus, and this is how you get the final product. So in conclusion, when I have a cyclohexanone and I react it with a diol, I am getting the protected product. And if I have this particular starting material, it's a kind of alpha beta unsaturated ketone, and I'm doing the same reaction. Here also we need a catalytic amount of H plus. If I do the same reaction with this particular starting material, I'm getting the protected product, no doubt in that, but the position of double bond will be shifted. And we have seen the mechanism for that just now. But if I want the product without shifted double bond, which reagent should I use? So I want my product without shifting this double bond. So the reagent you have to use is the protected OH group. You can use the protected OH, which I have discussed in my protection deprotection alcohol strategy. So you can do the TMS protection of both the OH groups. Okay, you have to use a TMS with leaving group like OTF, and this reaction is done using DCM at minus 78 degrees Celsius, and this is how you generate the protected product without shifting double bond. So you have to take the protected diol. Okay, so I hope I'm clear. So these three things you have to remember. You can directly protect your ketone by using diol. If you have this kind of particular system, if you use diol, the double position will be shifted. You will eventually get the protected diol, but the double bond position will be shifted. If you want to stop that and you want to selectively just protect this one, you have to use the protected diols like TMSO. So now let's move forward and try to solve some problems based on protection reproduction strategy of aldehyde and ketones. Okay, so the first problem we have. So this is my starting material. And I'm reacting this with diol in presence of a source of acid. So what is the product? So this is the first question. So we know that ketone is more reactive than ester. So this is my ketone and this is my ester, and we have to do protection. So ketone is more reactive, so we are going to go ahead and protect this ketone selectively. And this will be untouched. So this is the product for this particular reaction. Okay, so next question we have. So this is my ketone and this is another ketone. Not really a ketone. If you look closely, this is a alpha beta unsaturated ketone. So if you have taken a note in my previous slide, you will be knowing that a ketone is more reactive than alpha beta unsaturated ketones. And if I do protection, let me do this time a 1,3 diol protection. So the product will be this one. And we are not going to touch the alpha beta unsaturated ketone simply because the simple ketone is more reactive. It's going to react first and will form the product. Okay, so here is another question for you. I want you to draw the mechanism for this particular reaction. Well, this is very interesting question. We have a dimethyl sulfide as one of the reagent in first step, and then in second step we have a diol, and then in third step we have a base, and the product we are getting, excuse me, so the product we are getting is this one. So feel free to pause the video and try the mechanism for this reaction. Well, this is a very interesting question simply because you are protecting a ketone in presence of aldehyde. If you look the product, you are protecting ketone in presence of aldehyde, which seems little unusual because aldehydes are more reactive than ketone. So ideally aldehyde should be protected if you are doing protection. And if you want to do protection for ketone in presence of aldehyde, these are the three reagents you have to use in a sequence. So what is the mechanism? Let's discuss the mechanism for this reaction. So we know aldehyde is more reactive. So if I do anything to this material, aldehyde will react first. So this lone pairs of sulfur will attack at this position, will form O minus, and we have C double bond O, OH. This will be protonated, and here we have SME2. So sulfur has 3 bonds, will get positive charge. Then in second step, you can comfortably do your protection for ketone because now we have no longer a aldehyde functional group. So this will generate a protected ketone Let me write this OH like O single bond H, because in third step the base will come, will take away this proton, will form a double bond here, and this whole group will again going to leave out as dimethyl sulfide. So we have a loss of dimethyl sulfide and we have simply generated the product. Quite interesting, right? So you are protecting your ketone in presence of aldehyde, although aldehyde is more reactive than ketone. So in first step, use dimethyl sulfide. This sulfur lone pair will attack at this carbonyl, O minus will form. Later it will be protonated to OH. Now you no longer have an aldehyde group. Comfortably protect your ketone into a ketal, a cyclic ketal. It's a cyclic system coming from ketone. So a cyclic ketal. And in last step, use base. So this will take away this proton, will form double bond. This whole group is going to leave and you have regenerated your aldehyde. So this is a interesting question. Okay, so here is a set of questions. So my starting material is this one. Here we have a carbonyl and I'm reacting it with a diol in presence of H plus ion. I'm getting something. You have to find out what is the product. In next step, I mean in different kind of reaction, I'm using this particular reagent and I'm getting product. In third set of reaction, we are using a thiol system in presence of, you can use acid or you can use Lewis acid like BF3. So what is the product? So feel free to pause the video and draw the product for all the three different reactions. Okay, so we have already seen these two. So if you have a free alcohol group and this particular molecule, so we are going to protect this ketone and we are going to shift the double bond at this position. So product will be, so we have a protected ketone, double bond is shifted here, and we have a methyl group here. So this is the product for this reaction. But if I use the protected OTMS group, the double bond will be intact and this carbonyl will be protected. So here the product is going to be this particular reagent. So this is the two products. So use free alcohol, double bond will shift. Use protected alcohol, double bond will be intact, and in both the cases the ketone will be protected. What is the product for this reaction? Well, straightforward, simple. Instead of oxygen, just keep sulfur. And double bond will be intact. I'm just replacing my oxygen with a sulfur because the only difference you can see, the mechanism is exactly going to be the same. You can use Lewis acid to chelate your sulfur or H plus ions and it will be later activated. So this is the product for this particular reaction. Okay, so let me use the product for the previous reaction, that disulfide product, because I'm going to discuss now the deprotection for that one. So we have this protected ketone. So this was my product from the previous step. Now I want to deprotect it and I want to get back my ketone functional group. So which reagent should I use? And for example, suppose I want to convert this to a hydrocarbon, then which reagent should I use? So we are going to see all of these reagents in detail when I will start the series of reagents in organic chemistry. So for time being, if I'm discussing deprotection, I should discuss these reactions. So if you want to deprotect your disulfide linkage back to ketone, you have to use the salt of Hg plus 2, like mercury diacetate you can use. So this will bear the Hg plus 2 charge. So if you use the Hg plus 2 salt, you will be able to convert this moiety back to ketone. Now I want to convert it into a hydrocarbon. Then the reagent you can use is a metal. You can use a ranitidine, for instance, in presence of H2 ethanol. And you will comfortably get back you will get hydrocarbon this time by using ranitidine. Okay. Let me give you one question here only. Suppose I want to convert this carbonyl into CH2. So which reagent should I use? Well, we are going to see them once again in future. For time being, we can do a Clemmensen reaction, right? Where you use zinc mercury amalgam in presence of H plus condition. This particular reagent you can use to convert your carbonyl into CH2. Or maybe you can do the Wolff-Kirschner reaction, that is your hydrazine, okay, in presence of base. So use any of this one and you will convert your C double bond O into CH2. Okay, few more questions. Okay, so this is my starting material and I'm reacting it with a diol. Simply I'm doing protection in presence of acidic condition. So what is the product? Well, here I have a ketone, I can protect this one. You have to do selective protection for one ketone. I am using one equivalent of this. Here I have a ketone, I can protect this one. So which one should I protect? Both are ketone, there is no sort of comparison between functional group. Both are ketone, you have to protect one of them. So I am going to protect. Let me draw both the products. Let me say this as A and this one as B. So if I draw A product, then this is the product. If I draw the B product, then this is the product. So which is the major product? Well, let me tell you, the major product is A. And the reason is this dimethyl group. They are causing the hindrance with the neighboring cyclic ketal. So that's why the product A is major, because there is no sort of hindrance between these two methyl group and this whole bulky group. So that's why the A is major product, because we have less hindrance as compared to B with incorporation of these two methyl groups. Okay, let me give you one more example. Let's say I have this acyclic acetal, I have this protected ketone, I have this protected cyclic acetal, and I am reacting it with, basically I am doing deprotection in H plus water. So we know this will be untouched, because if you want to deprotect this one, you have to use the mercury salt Hg plus 2 and you will get selective deprotection of this one, and rest will be untouched. But if I am doing deprotection with H plus water, this will be untouched and one of them will be hydrolyzed. And we know that acyclic acetal or ketal is faster, will react faster, will faster deprotect in presence of cyclic acetal ketal. So now we know the product. So this will be selectively deprotected, because this will cleave faster as compared to the cyclic version. So the product will look like this one. So this is the major product for this reaction. Okay, so that's it for today, and we have discussed in detail all the protection deprotection strategies for aldehyde ketone. We discussed the important questions regarding the exams, and in future we will discuss the protection deprotection for carbonyl groups like esters, acid, etc. We will also discuss the alkyne functional group protection also. So that's it, and thank you for watching.